Okay, so I messed up the Zoom meeting recording again, so I will be recording this. We're doing 10.3. 10.3 is on chords and arcs and their relationships. Just to go over what a chord is, as a reminder, remember that a chord is a segment with endpoints on the circle. So that means any chord divides a circle into two arcs. A lot of times these two arcs are major arc and a minor arc, major and a minor. There is one case though where it doesn't result in a major and a minor arc, and that case would be, that exception is when the chord is a diameter. So if the chord is a diameter, then it will divide the circle into two semicircles. So just to see what we're talking about here, let's sketch it out. Let's do two circles. One circle is to show that we have a chord, the endpoints on the circle divides the circle into a minor arc. Oops. That says minor, sorry. And the other arc is a major arc. In the case that it's a diameter, so we have a center, the diameter goes through, it divides the circle into two semicircles. So we go over three theorems. The first theorem is called the congruent corresponding chords theorem. So in the same circle, or congruent circles, two minor arcs are congruent if and only if, that means this is biconditional, the converse is true, if and only if their corresponding chords are congruent. What does that look like? That looks like, so we have a circle and we have two chords. If the two chords are congruent, then the arcs are congruent also. Now, yesterday we talked about arcs and the central angles and how they have the same measure. So if the arcs are congruent, that means their central angles will also be congruent. So if I draw in a central angle to these chords right here, then this angle is congruent to that angle because the arcs are congruent. So that means all three of these are connected. We have congruent central angles. Then that means the arcs are going to be congruent, which now today we're adding in chords are now congruent. Okay, the next theorem is called the perpendicular chord bisector theorem. So if a radius or diameter, And when we say radius or diameter, we're actually just looking at segments that start or pass through the center. So sometimes the segment doesn't go all the way to the circle, so it's not technically a radius, but since it's passing through the center, we could consider it a radius or a portion of the radius, and that still counts. So if the radius is perpendicular to a chord, then the radius bisects the chord and the arc. The converse is true too. So the converse is true. So if the radius bisects the chord and arc, then it is perpendicular to the chord. To show you what this looks like, we have a circle, we have our center, so we have circle E. Radius and a chord. Let's label this D, F, G, and H. So we're saying that EG is perpendicular to DF. So I could draw that in. EG is perpendicular to DF. Now that means that therefore the chord DF is bisected. So DH is congruent to HF, which also now means that arc DG is congruent to arc GF, because the arc is bisected also. So whenever you see a radius or diameter or a segment coming from the center and perpendicular to the chord, then that chord is bisected, so those two are congruent, and the arc is bisected also. Why is this true? How do we know this is true? Well, if I draw in this radius here and draw in a radius here, I just created two right triangles. Given that this is a right angle, this is a reflexive, EH is congruent to itself, ED is congruent to EF because those are radii. All radii in a circle are congruent. So those two triangles are now congruent by hypotenuse leg. So hypotenuse leg, that means DH is congruent to HF, CPCTC. That also means that this angle here is congruent to this angle here. And those are central angles. So that means this arc is congruent to this arc. That's the proof of that theorem. The last theorem we're going to go over is called the equidistant chords theorem. Equidistant chords theorem. So in the same circle, or congruent circles, two chords are congruent if and only if they are equidistant from the center. Okay, I'm going to draw this one bigger. That's okay. Okay, so we have two chords, chord here, and a chord here. These two are congruent if the distance, now distance we represent with a perpendicular. So draw a perpendicular, distance from the center, perpendicular. Distance from the center, perpendicular. If this is congruent to that, they're equidistant, that means this chord is now congruent to this chord. How do we know that? Well, again, we could draw in the radius, congruent, congruent, right angle, radii are congruent, hypotenuse leg once again. So that means this segment CPCTC is congruent to that. The previous theorem says it's bisected, so congruent addition, those whole chords are congruent now. Okay, so we're going to do some examples now. So we have our circle, let's draw a diameter, and a chord, J, H, N, K, L. I'm going to tell you that this is a right angle, and NK equals 7. Measure of arc HJ is 11x. Measure of arc JK is 70 plus x. Find HK and find the measure of arc HK. So this is segment HK and this is arc HK. This is a video, so you can pause. You should have this equation and plug it back in. You'll get 14. Well, 14 is actually coming from just the diameter. This is a radius or diameter perpendicular to a chord, so this is bisected. So this is 7, this is also 7, which makes HK 14. So that actually didn't require that equation. The equation is for the arcs, and when you plug everything back in, you get 154. Keep in mind this is congruent to that. Another example. My circles are getting better. Chord, chord. Tell you this is a right angle. This is 12. This is a right angle, 12. A, B, C, D. So we have circle O. AB is 7x minus 3. CD is 5x plus 7. Find the radius of circle O. So we want to find the radius. There's only, there are many options on where we can draw in the radius, but there are only like 4 places that would be the most helpful for us, and that would be drawing a radius to the endpoint of the chord, because then we just create a right triangle. So we know that these two chords are equidistant from the center, so that makes the chords congruent, so the measures equal each other. That makes x equal 5. Plug it back in, and we'll get that this whole chord here, the whole chord is 32. We know that if a segment coming from the center to the chord is perpendicular, then it bisects. So that makes each of these 16 and 16. And now I could find the radius, r. You could do a squared plus b squared equals c squared, Pythagorean theorem. Or you could see that this is a triple. So radius is 20. Another example. That wasn't that great. Chord, radius, this part, oh, I didn't draw it to scale. That's 8 and that's 9. We have circle R. Find AB. So once again, we're going to draw in the radius. Oh, I should have told you that this is a right angle. Sorry. So that's a right angle. The radius should be drawn to the endpoint of the chord to create that right triangle. We don't know the radius, but we do know this radius is 17. I mean, this segment is a radius, so that makes this segment also 17. So now we have this right triangle. That's 8, 17, and x, let's say. Ooh, that looks familiar. That's a triple. So x equals 15. This is perpendicular to the chord, so that means these are congruent. So AB is 30. Now I'm going to give you some examples that don't have a picture. So you have to come up with a picture. So this kind of tests your vocabulary and knowing all the parts of the circle. So the length of a chord is 48. The distance from the center to the chord is 7. What is the radius? Okay, so I'm going to draw the circle. And draw the chord. The length of the chord is 48. So this is 48. The distance from the center to the chord, distance is a right angle, is 7. A segment from the center, so the radius to a chord, perpendicular, that means I just bisected it. So this is 24 and 24. Find the radius. This is 724. Oh, that's a triple. But if you didn't know that, you can use Pythagorean theorem and get 25. The last example, distance from a center to the chord is 12. The radius is 20. How long is that chord? Okay, so circle. Draw the chord and distance from the center. Distance is 12. I drew from the center to a chord, so I bisected that. The radius is 20. How long is this chord? This is another triple. If you didn't see it, then you can use Pythagorean theorem. This is 4 times 5. This is 4 times 3. So this must be 4 times 4, which makes this 16. A lot of people are going to write 16 as their answer. That's not what the question was asking for. The question is asking for the chord. So if this is 16, this is 16. So the chord is now 32. All right, so keep checking my website, or I'll email you with updates because I feel like things are going to change soon. So yeah, keep checking, or I'll email you. Okay, see you tomorrow. Bye.